Hello everyone. In today's lab we are going to solve this circuit. This was also part of the lecture. This is an example from your book, example 10.6 from the 10th chapter. You guys have solved this within the lecture. So in this circuit, which is an example 10.6 from the book, you were asked to find out the impedance of the circuit, but without the voltage source. Now a voltage source was introduced with this specification 40 sine of 5t, and then we expect to see the current of this magnitude. It should be having an amplitude of 6.15 amps with a phase angle of minus 50 degrees, something like that. Now if we look at the inductor voltage and current, this is the inductor current and voltage expected, of course not in the cosine form, in the sinusoidal form. Now this is important here in Cadence. In Cadence we define the voltage sources in the form of the alternating voltage and alternating current source in the form of sinusoidal voltage, not in the form of cosine voltage sources. Now this is important when you're trying to configure a voltage source. If you're trying to solve a theoretical problem from your book, normally your book assumes the voltage source in the form of cosine. When you would like to do it, when you would like to implement your circuit in Cadence, please try to change them into sinusoidal waveform. This will help you to find out the right phase angle as per the theoretical calculation of your book. All right, this is very important. Again, so we are going to solve this problem, and for this problem let me connect the circuit first, and then I'll come to the voltage source, and I'll let you know how to configure the voltage source, a sinusoidal voltage source with some phase angle. All right. So let's quickly move to the library manager. So I'll instantiate a resistor first. So I'll instantiate a resistor. Okay, we have one resistor here and another one here, and then we'll instantiate a capacitor. Okay, instantiate a capacitor. We'll rotate it and put it over here, and then we'll instantiate an inductor. Okay, R for rotate, and then we'll put the inductor over here. All right, now look at the circuit diagram again. We have one resistor, two resistor, capacitor, and inductor, and another capacitor. All right, so remember, if we want to copy, either we can instantiate or we can hit the C key on the keyboard. Once you hit the C key, your cursor is in the copy mode, so just click the component that you would like to copy, and you see it is already attached. Just clicking one single time, you have the capacitor. Hit the rotate key, put it over here, and then instantiate the ground. I'll put the ground over here, and then instantiate a V sine. You see, sinusoidal, for the sinusoidal waveform, we always represent them as voltage of sinusoidal voltage. So let's put it over here. Okay, let's wire the circuit. Capacitor, okay. And the last capacitor here, and yeah, I think that's what the circuit looks like. Okay, yes, so let's do fit this circuit and then check and save. One warning. Okay, what is the warning? Dot on crossover, the same thing. I mean, it thinks that the system is thinking that you would like to connect your resistor directly to the ground, but accidentally you place it here. But that's a warning, and we know what we're doing. We wanted the things to happen this way. Okay, with this, let me quickly label the label. So I'll go I'll label the voltage of source, and then voltage of source will be the actually voltage of capacitor and resistor too, and then voltage across L. I'll put a V underscore L. Okay, that's the voltage of inductor, and then we'll have the voltage of RL. All right, the last node. Let's see. So that's what I'm calling as a voltage source. This is the voltage of inductor, and this is the voltage of this whole node. So that's how I've done the net labeling. Now let's see what are the values. We have 200 millifarad, 500 millifarad, 10 and 6, 200 and 500. So I'll hit this one. Q capacitance is 200 millifarad. Okay, and this one is 500 millifarad. And then we have 2 Henry. And then we have resistances as 10 and 6 ohms. So I'll click this one, Q 10 ohms. And this one is 6 ohms. Now for the voltage source, let's go to the voltage source. Now, as you see that the sinusoidal signal is given as sine of 5t, and then from sine of omega t, we know that 5 is the omega radian in radians per second. 5, we know omega is equal to 2 pi f, so the frequency will be 5 divided by 6.2 hertz. Now please note that in Cadence the frequency is not in the radians per second, it's given in the hertz. So you'll always have to find out from omega what will be the system's frequency. So it's 5 divided by 6.28. That's the first thing. The second thing is the phase angle. So the phase angle in this particular question, the phase angle is not important, but you can configure it. I'll show you how to do it. Why it's not important? Because every other phase angle in the component is relative to this phase. So this phase can be any phase, all right? It could be 0, it could be 50, it could be 90, whatever. And then everything else takes the phase relative to it. But let's suppose that if we had two voltage sources with two different phase angles, in that case you would definitely convert them all to the sinusoidal voltage sources with their corresponding phase angles and configure them. So right now we see that 5t with a 0 phase angle, 40 is the amplitude, and frequency is this one, 5 divided by 6.28. Let's start working on configuration of the voltage source. I'll hit this one with the Q. I'll go down there here, amplitude. So amplitude is 40. Initial phase for the sinusoid, this is the initial phase that you would like to write. I don't have a phase, I'll still put the 0 here. The frequency is 5 divided by 6.28 hertz, right? Was that 5 divided by 6.28 hertz? Okay. Yeah, you can write the frequency in this way, right? So let me amplitude is 40 and initial phase is 0, and this is the frequency. All right, okay. So our voltage source has now been configured. Let's just check and save. Should have only one warning. Okay, let's go launch ADXL, create new view, lab 3 example. Yes, this is how I have named it. We'll initiate a test. Okay, and we'll go to setup and environment, 64-bit. Okay. Now you will do here, we'll learn a new thing here. We'll go to the outputs and save all. I'm sorry. So what we're trying to do here, we are saying that we would like to select all the outputs in the circuit. So I want to save all the systems, all the output powers, and the probe level signal will be 3. Okay, so just we don't have to know that what does that mean. The sub-circuit probe level is that how deeply the signal is looked at. All right, select device currents all. All right, this is how you will be configuring your saving all outputs. So what this is going to do, it is going to analyze all the voltages, currents, their signals, and it's going to analyze all of them and save them. All right, I'll do OK. Now I'll do the transit simulation. For the stop time, I'll take 100 seconds. So now I'm taking 100 seconds because I know the signal has the transient signals for a long time. I've checked it. It stays, this transient signal stays for like 50-70 seconds. So instead of coming back and changing the values, I'm just doing it stop. Time is 100 seconds. Use a conservative. Say OK. And once you've done, you don't have to look at the outputs because you have already saved all the outputs. We just close this and then we run simulation. We'll see if there are any errors. There are no errors. There are only 5 notices. All right. Right now we have not selected anything important. So I'll do here, I'll go right click this one. I'll go to the direct plots and I'll say plot me the transient signal. All right. The transient signal, it opens the window where the transient signals will go. And now I would like to see what transient signal I would like to look at. So let's see at the voltage source. We know we've configured it to be 40 amps. So I'll click this one. This is the voltage and current. So current through the voltage source is going up. So I'll select this node here. Once these two signals are selected, I'll just hit the escape key and then I can see within this window these two signals can be seen. All right. I'm sorry that direct plot was not okay. Now, as I was telling you guys, that you see that the purple line, that there are transients present throughout the time. All right. So just to avoid that, I've selected more than like nearly 100 seconds because what I see that the signals just get stable after this point. You see. So I would like to look at the this last area. Okay, the delays. Okay, let's look at this. Oh, we will be also be verifying that you know, the thing that we've been studying in the class, that in the inductor the voltage leads current by 90 degrees, as well as in the capacitor we know that the current leads by 90 degrees in the capacitor. So we'll also look at that very quickly. So if we see that this is the voltage, as you can see here, the 40 is the voltage, and then the current. For the current is something that we've been looking for as part of the answer. So we see that the current is 6.15 amps with an angle of phase shift of minus 50 degrees. So we are going to confirm that if this is what we are seeing here or not. So the purple line is the current. So let me just quickly make it a little bit thicker. Okay, and I will like to take a little bit less of the signal. So one way to properly align the axis, since I zoomed it a lot and I see that nearly at 89.174 is the point where the green signal, which is the voltage signal, becomes 0. So I did right click on the x-axis, and then looking at the axis properties, I selected axis limit minimum as 89.176 and maximum as 92 seconds, so that I can look at the two waves at least. All right, so when you do that, you will be able to isolate the green signal here, the voltage signal at the nearly 0 point. So after doing that, I just took a picture of that part, and it's just to show you the estimation of the angle. So, and I did it with the snipping tool. Definitely, I just quickly wanted to do it instead of doing all this library manager and using mobile extreme and stuff. Okay, so I took the picture, took it to the PowerPoint here again, just to show you guys. So now we see that the green signal is nearly 180 degrees. All right, so we have the 360 degree, we have the 180 degrees, and from the middle I just took a kind of middle line, which is the 90 degrees. If you see that from 0 to 0, this signal, we can see that it is nearly above, a little ahead of the middle of this whole line. This whole area is 90 degrees, so we can see that this is not exactly 90 degrees. In the middle, it's not exactly in the middle here, which would be 45 degrees. So you can say that in an estimation that this is nearly 50 degrees, which is what we are looking at in our main solution. So it's like 50 degrees, right, of an estimation of an estimated phase angle difference. So I just want to show you guys that how does the system takes care of that. Again, 90 degrees somewhere in the middle here at this point. All right, so 90 degrees somewhere here. So in that case, the 45 degrees should be somewhere here, and then we have it this purple magenta current waveform a little bit ahead of it, which means it is like around 50 degrees. So that's one way of looking at the output, which we were looking at, which was at 6.15 amp, the phase angle difference. Now let's look at the voltage across inductor and current. It should be 46.6 volt and 4.6 amps. So let's see how to do it. We can go to our virtuoso. Okay, all right. We can go to the okay, here's our signal. Circuit diagram. Go to ADXL and then right click, and then you can say that from the direct plot. Okay, guys, you are looking at the delay. I mean, if you have this much delay, then this is acceptable. I mean, this is the delay we have to live with. Go to the direct plots, okay, and then go to the transient difference. All right, why transient difference? I'll show you. I'll let you know. So as you see that if you want to find a voltage at this point, you need to take a difference of this voltage from this voltage. Only then you will be able to find out the voltage across inductor. All right, so otherwise, if you're trying to find out the voltage at this point, it will just give you the voltage of this node in reference to the ground signal. All right, but we want the voltage across the inductor, so we'll select this one. We're finding the difference, and this one. All right, and hit the escape key, and then you will be able to see the voltage of the inductor. All right, now this is the voltage of inductor, which we can see is actually, as we see, the 46 point something voltage, and the current should be 4.6 amps. Now what I want to do, I want to show you guys how to manipulate few things here. So I'll go to ADXL, and from this replace, instead of replace, I would say that append. All right, I'll go with append. Append means to attach my new signal, and I'll go right click again, and then direct plot, and then the transient signal. All right, so I'm appending my transient signal, which will be the inductor current. Here, click at this node. All right, and hit the escape key, and you will see that we have the voltage and current together here. Both of them got the same color, so I'll just right click and give it a different color. Color it magenta, and then this one can be yellow. Color this one to be yellow, and give it a thickness. Thick. Okay. Similarly, I'll make this signal to be a little bit thicker. Okay. Now this is the voltage and current and voltage and current through the inductor. Now we see the magenta color is the voltage, and the voltage we can see at the top is 46.4. all right, that is 46.6 is the voltage, and the current should be 4.66 amps. Okay, this is the current over here, and you see the peak current here is 4.69. I'll hit the M key to get the marker. All right, that is 4.6 amps. Now, as I said, that we'll look at the estimation of the fact that in inductor the voltage leads the current by 90 degrees, and as we've done before, so here's the 0 and here's the 0, and if you see that it is nearly at the middle of this, so the time when this thing touches the 0 is 89.49 is the time when the top is 89.49 is the same time when we have 46.4 volts. So looking at this, we can estimate that the voltage is leading the current by 90 degrees within this signal. So that's how to look at the phase differences. All right, and we have somehow done the solution for here 4.66 with the phase angle of -90 and this 0.9 degree, and together the difference between both of them is a 90 degree phase difference. If we had a capacitor, okay, we can actually look at the capacitor tool. Let's quickly, let me make a sub window. Okay, let me make a sub window. Yeah, create a horizontal sub window. Okay, so there's a sub window. Now there's something I want to show, not this important, but you can actually pick up a signal. All right, I can pick up an IT signal and just drag it and put it here, and it's a way of just dragging the whole signal and bringing it to the new window. All right, this is one of the things you can do. So what I'm going to do, I'm going to replace, I'll look at the voltage and current of the capacitor, one of the capacitors, in the new sub window, and Excel, and I'll go direct plot transient signal. It is going to append to my last window. So I want to look at this capacitor, right? So I'll look into the voltage of the capacitor, which is this one, and the current through the capacitor, which will be this one. All right, once you've done that, hit the escape key. Here are the two signals. So we have the current of the inductor, capacitor, and so let me turn off the view for this one. So invisible. Okay, now we have the voltage. The green is the voltage VRL, which is the voltage of the capacitor, and the current through the capacitor is the magenta color. And again, if you see, the difference is 90 degree, where the the current is now leading. So in capacitor the current leads, so we see that the magenta color is at 0, while this current, the voltage signal is coming still following that. So the current is leading the voltage by 90 degrees. So somehow we have looked at all the plots, all the windows, and how to solve them, how to create different sub windows. You have also seen okay, I'm sorry, the delay, that how to save all the properties of the signal, and then you can just use a transient signal. You can go to the direct plot and you can select the transient signals or transient difference or transient sums. You can do many things. How did you set it up in the ADXL test environment? So with this, our lab comes to the end. I'll just quickly show you what I've selected. I've selected the problems from your homework. You guys have already done that. Okay, here's the problem. This is one of your homework problem. Look at this. We have the two sources here. All right, with two current sources, we can see them, and they both have a different phase angle. So they are both defined in the cosine. So please turn them into sinusoidal waveform, and accordingly change the phase and set your initial phase accordingly. All right. Similarly, for this one, I've given you the omega is 1.2 radians per second, so you can find out the impedance of these elements here. And we have I1 and I2 can be here. Yeah, I mean, so the current sources have a phase difference too, and thus you should be properly configured. So I've specifically told you guys about this, so please make sure that you are taking care of this thing. All right, with this video comes to end. Thank you very much.